Okay, so now that you've already seen the freestyle, you already recognize the limit notation, and we're hopefully ready to actually tackle some graphs. So let's see if we can tackle these graphs. And I'm going to try and let you know what I'm doing in a particular color at a particular time. And also, I'm going to work on this graph several times. So be very careful about what you decide to write right here, because as we go through this whole first page, we keep coming back to this graph over and over again. So first thing I want to look at is what is happening to my function at -4. And I want to remind you of that word approaching as a limit. I want to approach. So I'm only looking at when I go to -4 on the x-axis, what I'm looking at is whether or not that function is approaching something from the left side and from the right side. And in this case, it definitely is approaching something, and that something is a height, and that height is 1. So remember, limits are a height. It's your output value, okay? Well, it's close to your output value. We'll see what happens as we move through this. Okay, so now I've talked about that one. I want to go ahead and look at -1. What's happening at -1? Well, there's a dot there, but that's not what the function is approaching. When I look at what we're approaching, I draw those two arrows. We are approaching a height of 4. Now, we will never get there because it's not allowed to be existing at 4, but it is definitely getting close to 4. Okay, so now I want to take a look at 2, number 2. And when I'm looking at 2, next is 2, I see that we have this unique situation again where we're approaching something from both sides, but that there's a hole there. And I got to tell you, I don't care. I feel like we are still getting close to a height of 1. So I'm going to write that down. And then I want to say what is happening when I look at x being 3. So here's 3, and notice, ooh, there's dotted lines here. And not only that, but look, this side is going down to -infinity, and that side is going down to -infinity. Ooh, guess what? That means we are going down to -infinity from both sides. And I'm going to come back to this and do a little star here because we want to make sure we come back to this topic of -infinity, just in case it's already occurred to you, well, what happens at positive infinity? We're going to take a look at that in a little while. So now I have this one last number, x equals 5, and at 5, I notice that one side of my function is approaching a number but never reaches it. The other side of the function is approaching a number, does reach it. But the point is that if I imagine that I'm walking on this, I'm a little person, and I'm walking on this, in order to get up to this part, I would have to jump. So I call that a jump discontinuity. And that means that the limit does not exist. They must match both sides must come to the same number. Okay? Now let's see if I can write on this graph in such a way that I don't ruin everything. Looking at -4, I need to find what the function value is. Is there a specific output? Yes, and it's pretty well defined. It is defined to be 1. I mean, there's a dot there, so I mean, I don't think that's weird, but you could see that it exists and it goes through that dot, and that dot has a height of 1. But what's happening at -1? Well, when I look at -1, then what I see is just a little bit different, right? I have these two arrows and they are approaching a height of 4. But when I actually am at -1, boom, I am also just at a height of 1. How strange is that? So then I want to take a look at the next piece and I say, oh, well, gee, I can approach a height of 1 from both sides in orange, but I can't actually get to that height of 1. So we say it does not exist, or we can say not in the domain, right? X equals 2 is not in the domain. That's a value that I'm not allowed to equal. I'm not particularly sure why. This is just a pure math example. But, from time to time, division by 0 is bad. Well, then you wouldn't be allowed to equal 2. So it's something like that is going on. Now let's take a look at the next number. And again, I'm going to mention, I see that I'm approaching negative infinity as a value, but can I actually equal a 3 like ever? The answer is no. Okay, I cannot equal 3. I could tell you a little bit about this function. So f of example, I could put in a 2.99999, and I get really, really super duper close to 3. And what I'm seeing is that I will get an answer of like negative a million, or maybe it's negative a billion, or maybe it's negative a trillion. How many zeros do I need to write to give you the idea that the output gets very, very, very negative? Okay? Still, the answer is I can never put in a 3 right here because it is not in the domain. Okay? It is not in the domain. But this time x equals 3 is not in domain. There is an asymptote there, so you're not allowed to equal that value. All right, let's take a look at number 5 then. The number 5, the input of 5. And I'm looking, and it is defined, and it's not defined down there. No, it's defined up here. And that height, I'm tracing back on the y-axis, is a 2. So there you go. Those are all of my limits and my function values. So I mentioned I was going to do this. I'm a little bit wanting to clear this all off because I want to make sure that I can see what's happening exactly at positive and negative 5. Okay? And so I want to see, look, sorry, 5 from the plus side, and that's this one here, and 5 from the minus side. So this is 5 from the plus side, and this is 5 from the minus side. And what I'd like you to imagine is that if you're coming in from the left, then you should use the negative symbol. And if you're coming in from the right, you should use the positive symbol. So now that we're looking at that, from the left, I'm approaching a height of negative 1. See, trace back on the y-axis. Here is negative 1. Okay, great. And looking at 5 from the plus side, I am approaching a height. Ready? Let me trace this back. It is approaching a height of 2. So that is how you do a one-sided limit. Now, as we move forward, we are going to talk about continuity. Limits go hand in hand with continuity. And you could say that a function is continuous where it can be drawn without lifting a pencil. Roughly, it means that continuous is connected. And we say that a function is continuous where its limit and where its function values are the same. So we take a look at this piece from the left, and we take a look at this piece from the right, and we check to see, is f of c defined at that point? And if you can say check, check, and check that they all equal the same number, then you can say that that function is continuous. Okay, so let's talk then a little bit about 3 different kinds of discontinuities that you can have. And I told you I was going to write on this a bunch of times, so here we go. This is, I believe, the last time. There's no discontinuity here. When I drag my pencil all the way across this, the only time I have to stop is right there at that point. And so I don't like to call this a hole. I like to call this, ready, a point discontinuity. And then I say, there's also something called a vertical asymptote. And so we have a picture of that, and that is at 3. And here's the last one. I already mentioned, if you can draw a dude and they would have to jump in order to get to the next segment, that is called a jump discontinuity. So right here is a jump discontinuity. And we've just now answered number 13. It says, list the x values of the discontinuities. And I'd like to do it in order, okay? So I would say that I have a point discontinuity / hole, ready? I'm going to clear this off so I can see everything. Make sure I don't miss any. There's a hole there and there's a hole there. So at x equals -1 and at x equals 2. So that's my point or hole. And then I have a vertical asymptote. Don't make fun of me. I know I say that wrong. And it is at x equals 3. And then I have this last piece, which is a jump discontinuity. And it is at x equals 5. Okay, so we have 1, 2, 3 pieces. The point constant discontinuity, the vertical asymptote, and the jump discontinuity. We have 1, 2, 3, and 4 of them all together. Okay, now it says discontinuities can be classified as removable or non-removable. And so when I see that there's a hole here but a point there, well, I could move that point up and then the hole would be gone. Right here, there's a hole and there's no point. Well, I could define a point and then it would be gone. So we say that removable discontinuities, ready? They're the same thing as point or hole discontinuity. You can get rid of it by defining your function there. Non-removable discontinuities occur when the limit of the function doesn't exist, such as when there's a jump or a vertical asymptote. And let me explain a little bit more of that. Again, I want to talk about this piece, and I mentioned that I was going to be. I'm going down to negative infinity, and I just want you to know that we as human beings, we can never achieve negative infinity. We have to keep doing it for forever. That's what forever means. So there's no way for me to get back to over to this side and come up from negative infinity in order to move on to the rest of the graph. So this is called a non-removable discontinuity. And by the way, when you're looking at graphs, so more on infinity, when you are looking at infinity, if you see a graph and one side of it is going up like this and the other side of it on the other side would also go up like that, then you can say that it is approaching positive infinity because they're both approaching infinity from both sides. But you still say that there's an asymptote there. So there's still an asymptote there. Okay, and so that's not a function that's defined, and that's not a value that's defined in your function. And that word looks terrible. On. So what if, though, it's occurred to some of you maybe, like, oh, well, what if I had a function that looked like this, where one side is going up and the other side is going down? You might remember, by the way, that we have seen such graphs when we talked about, important graphs to memorize. I feel like this guy right here is like 1 over x, and this guy right here would be like -1 over x, right? So in this case, the limits don't match and they don't agree. Therefore, it does not exist. Okay? So keep that in mind. It only exists if you say that they're coming together. Now, if you want to argue about it, I will tell you a secret, okay? Which is that in this case, on the AP exam, you can actually call it does not exist. Because some people sort of argue that because there's an asymptote there, that it's not continuous. It's not in the domain. So they want to say that the limit doesn't exist either. And on this one, you also can say that it does not exist, because that's like a controversy in the math world where we don't all agree on the same thing. So from our freestyle, you will recall that when you're doing just a plain old limit with a well-behaved function, all you have to do is plug in the value that you're approaching and calculate that height. And so in this case, 27 plus 2 ends up being 29. Here, we can factor some stuff. We know we could simplify some things, but honestly, it's not necessary because remember, the asymptote here is when x equals -1 and
I don't care about -1 today. I care about +1. So I'm going to say that I have 1 squared plus 1 over 1 plus 1, which is going to end up being 1 plus 1 is 2 over 2, ends up being a 1. For number 17, I remember that cosine is this very well-behaved function, and it goes down, it goes up again, it goes down, it goes up again. It has no holes or asymptotes. Well, I mean, for number 17, I remember that it's a very well-behaved function. It goes down, it comes up again. We have it's pretty easy to see right away that we do have continuity on this function as well as sine. And so I can just plug in that pi over 3. So I'd say that I have cosine of 2 times pi over 3, which is the same thing as 2 pi over 3. And I happen to have this one memorized, which is zero .5, negative zero .5. But you would put it into a calculator. Or if it's a free response question, you don't even have to put it into a calculator. You could just put a box around it like that. Okay, so then I'm looking at piecewise functions. A one-sided limit evaluation is often necessary. And so for number 18 and 19, I could do the algebra, and I am going to. But before I do, I would like to talk about what it looks like as a graph. Okay, so number 18, take a look at it. Do you think it has continuity? Yes or no? And I'm saying that I believe that it looks like it does, and here's why. I'm turning these both into purple. Yeah, look, they meet up nicely. So you could trace all the way down to here, and then you could trace all the way back up around. And right here, at this point, this function hits a height of 3. This function hits a height of 3. And since they both hit the same height, they're they're perfectly aligned. So algebraically, what does that look like? I want to know what the limit is when x equals 1, so I'm going to plug in a 1. So I have 4 minus 1, and there I get that height of 3. And here I have 4 times 1 minus 1 being squared, which is 4 minus 1, which also equals that height of 3. So boom, yes, that limit exists, and the answer is a 3. I only have to put a box around one of them. You know what I mean? Don't have to put a box around them both. Um, right here for number 19, let's take a look at that graph. And I'm saying that sometimes things don't line up perfectly. You could see you have a jump discontinuity here. So you go all the way up to here, and at 1, your height is 2, and here your height would be 1. And so these two things don't match up. Now you could put it into Desmos and see that it doesn't match up, or algebraically, how does that work out? I do 3 times 1 with 1 being cubed, and that's going to be a 3 minus a 1, which is a 2. Notice that we saw that height before. And then here I plug in the 2 times 1 being squared and minus 1, which is the same thing as 2 minus 1, which gives me a height of 1, which means that the limit is that it does not exist. Heights do not line up. And you could put here in these notes, by the way, say check in Desmos to see. Okay. And I just want to recap really quickly that the reason that we know that there could be a jump in the graph at 1 is because that's where the break is. So you have the limitations on domain are occurring at a specific spot, and you have to list that right here in the piecewise function so you could see what it looks like. And that means that if that's at 1, that's where you have to check both equations. Again, here, that was also at 1, and that is why I had to check both equations, is because I knew that there could be a jump there. Also, we looked at the graph, so we cheated. What if, though, for like number 20, it says for the same g function, the limit of g of x as x approaches -1, -1 is not where the jump is. And so if we looked at the graph, we could actually find that height just by going over to where x is -1. Algebraically, though, how do we do that? It basically, it looks like this. So we say we want to know when x is -1, and we have to figure out what conditions are we under when x is -1. So I have these two different functions, and I'm going to have to pick one of them and plug it into that. But I just want to point out that if things are greater than 1, then they aren't as low as a -1. This is where it says we need to be less than 1, so we can go down to 0, we can go down to -1, we can go down to all the negative numbers. And so that's how we calculate this limit. So the limit of g of x as x approaches -1, I can just break this down into this: 3 times 1 minus 1 being cubed, and find out 3 times 1 is 3, and -1, sorry, times negative of -1 being cubed, that ends up being 4 negative signs. So I could just add, oh, sorry, that's a -1. I can just have a -3 here and a +1 there, and boom, that's how I get a height of -2, which, let me show you graphically. Here it is. That's where -1 is, and that's the red function. The red function was my 3x minus x cubed, and I could grab that height of -2. By the way, I will mention that if you do this sort of notation without a function being assigned to it, it's not as useful as if, say, what we called a g of x. You can't have two g of x's on Desmos, but you can have like a g sub 1 of x and a g sub 2 of x, or you could just change it to a different, function name altogether, but you still know that this is the two pieces. So by the way, when I am calculating problems on the AP exam, if I have time, I will cheat and just throw it into Desmos right here. Boom. That's how I got that height of -2. This height right there. So we're doing an activity on the greatest integer function, also known as the floor function, in class, but real quick, just so that, if you forget what we were doing, you remember this is a rounding down equation. It rounds everything. Sorry, down. And so if I have a value like here where it says 1/2, I check to see what's happening at a half, and it tells me that the height that I'm at right here is a 0. So it took a half, 0.5, and it rounded it down. And then I find out what's happening at 1. Well, there's an open hole here, so I can't use that. So I will say that I'm just at a height of 1. And that's because 1.0 gets rounded down to 1.0. And I also think it's worth mentioning that you could set a function in Desmos to be the floor function, and then you can plug in whatever values it is that you're interested in using. So k of 3.25, you would get a 3. You also, by the way, could create a graph of this. And so I want to add a new page. I feel like I'm getting out of practice with this thing. Okay, so I want to add a new page, and I want that to be a graph. And so I'm going to say in here, I had defined k of x, and there it is. Boom, that's my floor function. Or you could just straight up type in floor, or for that matter, ceiling. That function also exists. Okay, and so now you can see those two. And that also, real quick, notice how this is red and that is blue. The ceiling is the red and the floor is the blue. So you could tell that blue is like shift to the left, to the right, but really the way you want to think about it is that the red is the higher value and that the blue is the lower value. Floors go down and ceilings are up.